Hey, good afternoon, everybody. How are we doing? We're going to get started here with some activity. So let's just load it up. Here we go. MuBot is awake, and we are going to start some activity here. We got activity 10, categorical variables and interactions, introduction to logistic regression. Now, what I want to point out right here is logistic regression. Hey, Taylor, good to see you. How many more activities, assignments do we have this upcoming week? For 320, we've got this one. I think we have one more activity. I think it's like one more activity. Let me look at the schedule. I think it's all planned out, is it not? Let me go look at that syllabus right here. So on the syllabus I see, and they look to be posted, so we do have upcoming activities. We might not do all of them. We probably won't go to activity 13. I don't think that. We'll probably do model building, so that'll be assignment 12 right here. So we'll go through model building, and that'll be the end. I don't think we'll do activity partition models. So we have up to assignment 12, and it looks like we have up to activity 12. So this is activity 10, so 2 more activities after this. You bet, Taylor. Thanks so much for the question, Taylor. 100 points. So it looks like assignment 12, activity 12. I think that's everything on track. That looks to be the plan. And then the take-home final, we'll be releasing information about that very soon. So stay tuned for information about the take-home final, review quiz, all these great things coming up right here. And today we've got some logistic regression. So let me know if you have questions. Great questions right there. We have right here, download and read the file of act10 wholesale.dat. This is on the file right here. So it should be in your working directory. Calling it whole, I think we have that code right here. So there's a bunch of food that was sold, and let's go here. This reads a CSV file, a comma separated values file. So it literally means that the values are separated by commas, comma separated values, and we have the name of the file. It's using the read.csv. It's a .dat file, which is a data file, I think. And then strings as factors is true because it's going to take whatever is words. And oh, it's not there in my working directory. I might have not loaded it into my working directory. Let's do this real quick. We're going to reload R. I think I was working out of a different working directory. Dun, dun, dun. So if you run into that problem that I just ran into, you probably don't have it in your working directory. Sometimes I load R from different working directories. Oh, let's go find out where Brian downloaded it to. So I have run into the issue where I do not have the file in my working directory. Let's go to, or it has a different name. It looks to have the right name. We're going to download the file right here. I'm going to move it. So you're not seeing me doing all the, oh, it's got a 1 on it. Does it have a 1 for you? People might be running into an issue right here that mine has a -1, and let me show this. So it has a -1, and that is working. So let me see if that's the issue with the file and correct that, because I'm showing a -1 on the file extension, and we don't want that. So let me go to edit, and it shouldn't be doing a -1. No, I think other people, I think it's because I've downloaded it multiple times. If you run into this issue, let me walk through the steps right here. So if you run into this issue, helping out with some Zoom stuff right there. If you run into this issue, make sure the file has the proper name. Mine has a -1 on it. It's the way it's downloaded with a dash to match the name that is in the working directory. Yours has a -1 also. Oh, let me look into this. Let's try to fix this right here. So put that -1 on there because that's going to be a big stumbling block for a lot of people. Let me look into this. Okay, let me fix this. Act 10 wholesale dat. Let me go to, I'm going to fix this. Good thing because I can see this causing a lot of issues. Let's insert a document, course documents, or I'm going to go to course document. Okay. And Act 10. There it is, Act 10, and we're using the wholesale dat. Oh, looks like someone re-uploaded it or something, so it got a re-upload on it. Try reloading the page now, and try when you reload it to see what it does. So go back, Taylor. Thank you so much for being here to confirm. Maybe I'll try downloading it again too. I've downloaded it multiple times now, and I think it did it. There it goes. Should be working. I re-uploaded it and made sure it didn't have the -1. It doesn't show it when you look at it. It doesn't show the -1, so that's really confusing. But it was like, everything should work. I'm in my working directory, right? So usually reset stuff, and you're like, maybe it's a problem with the file name. So the file name had a -1, yours had a -1, you can add the -1, but we've corrected it now that when you re-download it, it shouldn't need the -1 to do it. You have to make sure that whatever this file name is the file name that is in your working directory. Like whatever the file downloads as, that has to be the name that you load. So if it says it's not there, it's looking for it and it says, I can't find that. And that's the error we're running into. So pretty good error to run into, making sure we know what's going on. Let's clear the global environment. I got tons of stuff loaded up from all the work, but let's go ahead and take a look at this data right here and see what we got. Now, the reason we're doing strings as factors is if we don't do that, you'll see it'll bring them in as strings. So watch right here. These are now characters. So the strings as factors will change it so that they're no longer characters. We're actually bringing them in as factors, which are categorical variables. So that's what that argument does right there, making sure we bring in the variables as categorical variables. We have a bunch here on just the different amounts bought, and let's take a look at the data. Good stuff right here. We've got retail in another region, fresh, and all the different types of values for the fresh, milk, grocery, frozen, detergents, and meat for the values for those items. Good data. Fit the multiple linear regression predicting fresh. Now, will we use linear regression for this? The answer's there. Or will we use logistic regression for this? Now, the question of using linear or logistic comes down to what is the y variable? Is the y variable categorical or is the y variable quantitative? If the y variable is categorical, we will use logistic regression. But the y variable here is not categorical, it's quantitative. So to fit the multiple model, predicting fresh from all the other variables, we want to go M save into LM. This is just saving the model into object M using the linear model. LM stands for linear model. The y variable is fresh, and tilde dot means all the x variables. Data equals is going to call the data frame that we're currently in. We have to call the data frame y tilde x comma data equals, and we have now fit our model. Let's go to the summary of it, and since we've called it M, we can just do summary of M. Now, when we look at this right here, let's take a quick look at this. What do we get? We get all of the significance of the coefficients for each individual variable. Now, retail has two levels. You can see it over here. Retail has restaurant or retailer. What kind of company are we working with here? So this is the retail company versus a restaurant company. But then we have region has three regions, Lisbon or Porto or other. And why do we not see Lisbon on here? Lisbon doesn't appear, nor does restaurant appear up here for type. Well, that's because they're the what? So hopefully you finished my sentence right here and know that each one of those, the ones that are missing, are the reference level. And the reference level is the first alphabetical. It's important to know that reference levels are for x's, categorical x's. These do not have reference levels because they're quantitative x's. They're just a coefficient for the value of detergent in the model and the weight of that variable when it comes to predicting the value of fresh. So we see here indicator variables for or Porto, which is a level inside of region, and other, which is a level inside of region. Let's go ahead. We see what the output is. Ooh, frozen is super. Is it negatively? Oh, it's not negatively related. People buying more frozen, or areas where more frozen is bought, more fresh is bought. Pretty interesting. So now, why would we do the drop one? Well, the drop one, we have to do the model and then test lowercase equals to quote f. So this is going to do a partial f test and do the effects test for us. Now, a lot of this is not going to be very interesting. I can tell you every p-value but one. Region's going to have a p-value of 0.0119. Milk's going to have a p-value of 0.1547. And I can tell you these values. And remember the milk right there, 0.1547. And there's the milk right there. And there's the rounded up of type. How did I know these? Well, if there's one thing in the model, we don't really just drop it in and out, but it could be theoretically, because the significance of milk right here is the significance of milk in the model, because milk only has one coefficient. So the drop one right here is really only important for one of these variables. The drop one right here will really only be used to examine the significance of which one. And that'll be the variable that brings with it multiple items. And the variable that brings with it multiple things is region. Region brings with it two indicators. So when we do the drop one, it takes all of region and removes it out of the model. It does a partial F by comparing a model with region and a model without region. So it has to remove these two indicator variables right here and says, these are removed from the model. So what is the significance for the difference of a model with region and without region. Be very careful. If you notice, this p-value right here is actually lower than both of those. And that's because these p-values are the significant difference that Oporto has with Lisbon, I believe it is, and other has with Lisbon. We are comparing kind of the difference between the indicators to the reference when we look at the p-values for these indicators. But the p-value here is the overall removal of the variable region with everything it brings. And once again, these p-values are not that interesting because milk only has with it one coefficient, so removing milk is the significance of milk. Removing type, since it only has two levels, brings with it one indicator, is actually just the significance. That's the same, just rounded down here, just the same significance. So really the only reason to look at the drop one right here would be to examine the significance of region, and region is not statistically significant. Region does not bring with it new information when we include all the indicators for region. The regression lets us understand, is there a difference in the average amount of money spent on fresh vegetables between two otherwise identical retail and restaurant customers with respect to the other variables in the model? What number in the regression output answers this question? If there is a statistically significant difference in the average, and if so, which type of customer spends more by how much? So we're looking at the variable right here. The average spend on fresh variable between to the other variable. Oh yeah. So it just depends right here. Is there a statistically different in the averages and what they're spending? And what we have right here is the significance. Let's look at the summary. What we have right here is the significance of the model, and the model itself is super significant. So when we're looking at the model, the whole regression as itself is super significant, telling us that this model right here helps us explain differences between these customers. Very, 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 very significant differences. Now, the p-values up here tell us whether or not these variables bring with them new information. Milk might be significant. Milk is significant. But why is milk not significant here? Well, by itself, it has information, but in a model with all the other variables in here, milk does not bring with it enough new information because now it has to compete against the other variables. So overall, the model, and this is the overall model right here, like as a whole, brings with it enough information. Interestingly enough, the p-value of milk right here is the p-value of the model because this is just milk working by itself. But if we have a full model right here, this is all the variables working together to see if they can explain differences between customers. The most significant variable right here is frozen. When we predict fresh right here, the most significant variable that brings the most kind of unique information that the other variables are not accounting for. The intercept, sorry intercept, no one cares about you. You're just a value when everything is equal to 0. It's not a very important value to look at a lot of times. The regression also allows us to probe where the average amount of money spent varies on the location, otherwise identical customers with region. Is the difference in averages between regions statistically significant? If so, which region had the largest average? Now, this is where you have to be careful. Region had with it how many levels? There's one of them missing. Once again, we can look at the data over here to see how many levels it has. It has 3 levels, and you can actually see the first alphabetical right here. Lisbon actually has a coefficient of 0. We don't really talk about its coefficient because the coefficient of Lisbon is just when Oporto and other are not there. So if we say it's Oporto, then it's going to be lower by 925. We would subtract that from the intercept. If it's region other, we would add it. Wait a minute. Which region had the highest, I believe it says? And if so, which type of customer spends the most and by how much? Well, it's kind of a moot point. The answer is region other actually spends the most, but remember we said it's not statistically significant. And review, how would we know that this variable as a whole, so I'll kind of pause right here if you're watching, let me know, how would we know if we take all of this out of the model, is this a statistically significant variable? And the way to know if it's statistically significant is to do the drop one, which is going to drop one of those out. Think what drop one says. It's dropping one of these out of the model. So it's going to drop just one, like region is a variable in the model, not the indicators, but it's going to drop all the indicators of region out and look at the significance of region. And region does not bring with it new information. So a model without region has about the same amount of information as a model with region because region is not statistically significant in this model with the other variables. So the last question is kind of not important because if it is statistically significant, which it's not, but it would be region right here. The one with the highest would be region other. Region Lisbon, which you can, EpicPen's hiding. Region Lisbon is actually in the middle. It would be between Oporto and other. Going down. The fitted model may be overly simplistic because there are no interactions. Ooh. Without interactions, the model assumes that the difference in average values of y when compared to otherwise identical individual customers in just x sub I is the constant of the x variables, independent of the other characteristic, other values of x's. So basically, one x doesn't impact another x. Pretty fancy way of saying that. Say, the way in which fresh explains, or excuse me, fresh is the y variable, the way in which milk explains fresh does not depend on the region it's bought in. So maybe like the way in which milk, like the coefficient of milk right here, would actually be different if someone was in region Oporto. So like you're in region Oporto, your coefficient of milk is actually this. You're in region Lisbon, your coefficient of milk is this. So the coefficients in the model might depend on other x's. So the certain coefficient we have right here might depend on another x. And that's what interactions would let us explore. Consider the interaction between milk and type. Include this interaction allows the nature between fresh and milk to vary between type of customer. Fit the model predicting fresh from type and milk with the interaction. The formula should be, well, there's the formula. Let's point out what this formula is doing right here. Once again, we're going to put this in the y tilde x comma data equals. There it is right there. And it's important to know a few things about this formula. This carries with it model hierarchy. When I say model hierarchy, what are you about to see? You're going to see the type-milk interaction. So you've got the interaction, and then you're going to also see type and milk. So we have the type, and we have milk, and we have the type-milk interaction. And what's interesting right here is we're interacting a quantitative variable on a categorical variable. So what we'll actually get right here is two lines with different slopes. They'll have different intercepts from right here, and they'll have different slopes from right here. And wow, we got statistically significant different slopes. Since the difference in the slopes are statistically significant, we are going to see less parallel lines. We're going to see more perpendicular. Now, how perpendicular? Sometimes they're a little less than you would think. Visualize model. Why are you not auto-completing? There we go. Ooh. Do I not have red class? I do not have red class. Oh, I reset R. That's why. Visualize model. And let's put our legend in the... It's not legend? Oops. Legend equals bottom left. I don't always use the legend argument. Oh, didn't do it. You can actually... Oh, it's loc. That's what it is. It's loc. It's location of the legend. Ooh, I don't like that. Let's go top right. It's blocking the screen right there. So here we are with our models. And what did we say would happen? We'd have two lines with different intercepts and with different slopes. Now, which line is more sloped? It'd be the retail. So the coefficient of milk is going to be positive, and then the interaction is going to be negative, because this is the reference line right here, which kind of has a reference slope to it. Like the slope of milk, which is positive, you can see it right here. The slope of milk is positive, is going to be lower if it is type retail. So what we want to be able to do, and this is a very good thing to be able to do, is write out the lines themselves. If we write out the lines, what would we get? Well, first, let's write the whole equation. The whole equation would be the easiest thing to write. You're just going to do intercept plus, and we're predicting fresh, so let's go here to fresh, equals, and the double dollar signs lets you get the equation notation from LaTeX writing, LaTeX, something like that. And then we're going to do this plus this times this, and then we're going to take the next one and do plus... And we'll put some spaces in here, times milk. Could have just written that, but no, why not? And then we're going to do minus, because this is a minus. And then we're going to take the interaction. I'm definitely going to change this to a multiply. It looks a lot better if you, because it puts the colon there for the interaction. But here's our equation. So our equation, and we can put some multiplies in here to make it a little clearer. This is, ooh, don't want that. This is our equation we have for predicting the amount of fresh food bought using type and milk. This is the whole equation. Now, when you have indicators, and indicators are for categorical X's, we are going to talk about either it is the type retail or type restaurant. So what we have to do now is we have to take and plug in only, so let's say retail equation. If it's retail, we have to plug in a 1 right here. And what will this change? Look at the equation. Oh, lost my dollar signs. Look at the equation right here. You'll notice that you're timesing this by 1. So that just turns into that. And you're timesing this by 1. So this is just this right here. And now you combined like terms. So let's go ahead and combine like terms right here. And to combine like terms, we would go in and we would take this number right here and subtract from it this right here, because these are just like terms. And that's going to make this coefficient. So I'm just put there, it's still positive. We subtracted that value of milk off of it. And then these two values right here are going to subtract because they have no values to them. And the 10,000 is the bigger one. And well, it'll still be positive after this. And there's the new intercept. So this is the equation. And then look at it. When you see it, does this line look down here to maybe hit, and we're talking about the red line because this is the retail line. We solve for the equation of retail. Does it look to hit about 6,000 and have a slope of about 0.2? Hard to see the slope, but the slope is positive. The easier equation to write is going to be the whole equation right here. Or excuse me, not the whole equation. Going to be the restaurant equation, because for the restaurant equation, the easiest thing to do right here is just to plug in zeros for where we see the indicators. So if we see type retail, it's not type retail, so we put in a 0. And it's not type retail here, well, that times 0 is 0. And then this times 0 is 0. And there's the equation. So that is the equation of the black line right here. And you'll notice the slope of the black line is higher and the intercept is higher. So we should see a higher intercept, which we do, and we should see a higher slope, which we do. So writing out these equations is pretty important right here. We could definitely have a test question or two saying, write these equations. We got the retail equation right here, and then we got the restaurant equation, and then let's show just the full equation. So there is the full equation without the indicators solved. There is the retail equation. And remember, the only thing that goes into here to the indicators are zeros or ones for the categorical variables to indicate it is that level. So consider detergents and regions in interaction. This interaction allows the nature of the relationship between fresh interaction to be based on it. Yep. And so let's do the same thing. Copy paste is your best friend, because we're going to go grab the copy paste right here and we're going to do the drop 1 because region has in it multiple levels. So now let's go right here, run our model, and you'll notice that we have right here interactions. Let's visualize it. We will get 3 lines with 3 separate slopes. And you notice there is some differences between the slopes. And I have no idea why it's doing this. It's really going off the screen. That's very interesting. I've never seen it do that. Very odd. Was there a point down there? I don't know, but it went a little bit crazy. Never seen it do that. So is this interaction here statistically significant? The answer is actually no. Visualizing the model actually gives you the drop 1 effects test. So another name for the drop 1 test right here is an effects test for our model. So this is doing the effects test on the interaction. And right here, you notice this p-value is right here. So very important, teaching to the take-home moment, is that the drop 1 can be done via the visualize. Now you'll notice we didn't get the other variables because it actually doesn't break model hierarchy. We have here the 2 interactions, which are the 2 different slopes we are getting, and we need to drop them both out of the model, but we can't drop region and detergents because these are kind of the things that build to the interaction. So by doing the interaction here, we're getting it. Oh, that's awesome. You're welcome. You're welcome, Adam. Thank you so much. Got a lot of emails and I was trying to catch up and I didn't get to everything last night. I feel bad. This is where we break model hierarchy here. I wouldn't do this, but now we get the 3 lines right here, but we don't have model hierarchy. Once again, we need detergents and region to carry through model hierarchy, and you see this in this model right here. Thank you so much, Adam. 100 points right there. I appreciate that. Everyone's so positive, even when I don't get to an email at night. It's really nice. People aren't like, ah! Oh, one time someone was like that. Fit a model. We're fitting so many models right here. Fit a model predicting fresh from frozen region milk and the interaction between region and milk. Starting with the output of summary, write the implicit equations. Okay. Let's fit a model. Fit a model predicting fresh from frozen plus region milk. What are you mad about, R? Don't be mad. And the interaction between region and milk. Okay, cool. I should do it. Write out the implicit equations. So once again, when we get the summary right here, it comes down to just remembering to do this plus this times this plus this times this plus this. And does it want the whole equation? Write the predicting fresh for the customers in Lisbon and the implicit regression equations for customers in Oporto. So if, and let's, oh, I don't like that decimals. To remove the decimals, I'm going to go to options SciPen equals 8, and we'll rerun the summary. Now we don't have decimals. I hate decimals. Hey, Scotty, see you next semester. Great to see you here, Scotty. Thank you so much, Scotty. Swing on by anytime. So we've changed it so we don't have the decimals now because decimals drive me crazy. But the SciPen right here is the scientific notation pen, so you can change it to better see what's going on with those decimals. If you change it to a long thing, you'll actually get some crazy looking p-values. Like change it to 20 and your screen goes crazy. But now I can see and I can easily add these. So what I'm going to do right here is a quicker solve of this. Right now, I'm going to know that if we change region or Porto, it's going to change the intercept because we'd be plugging in a 1 right here and we'd subtract this from the intercept. Now, you can't be in region or Porto and region other. You're either in Lisbon, which would be 0 for these, or you're in one of these. And then we're also going to change the slope of milk, the coefficient of milk, and it's going to become more positive. So the most negative line, you can see it, is Lisbon. Lisbon actually has a negative slope, and then region or Porto has a little more positive. There's our Porto, and then region milk actually has, or region milk, region other. Region other has the highest slope. Interestingly, it should be, should be. I'm doing the math on this. I think, let me revisualize this. This is my mathematics. Interesting. What's going on? Region milk or milk has this coefficient. Oh, okay. Reason being is I don't think this is the visualization. Let me check. We can't actually visualize this. I stand corrected. Okay, good. That's not the same visualization. Reason being, I didn't see, I was like, something doesn't make sense with the visualization. If you look at it, Colin, good to see you here. Thank you so much. Yeah, you were saying how you just got back to campus. So good. How did I not see that? Colin, so good. Thank you so much. 100 points, Colin, right here too. We can't visualize this because there's multiple X's in a way that we just can't make a good visualization. So that visualization you were seeing a second ago, I was like, that doesn't make sense. And it didn't. And I had a different equation. We've just done so many models. So let's go right here and let's put in the variables. Now we are predicting frozen equals intercept. And now the intercept, if we're doing Oporto, so let's do Oporto. With Oporto, we have to subtract from the intercept this value. So because remember, we're plugging in a 1 for Oporto here, which is going to make it a negative value. Or give you that value. And then frozen is just going to be multiplied by this. There is no interaction. So frozen is just this right here. And we just take the values, do that for frozen. This is going to be a 0 because remember, we're in Oporto right now. Milk is going to have its coefficient, but milk's going to have a higher slope. We are in region Oporto, so we need to add to this because we're going to take the interaction right here and add to it this. You're just plugging in a 1 for this and solving through like we did earlier. And this is the new coefficient of milk. Once again, review the earlier part of the video. I kind of want to, I want people to practice this right here and see how it works, because when you get it down, you can solve the equation a lot quicker. Check out the earlier part of the video where we did a step-by-step solving out the full equation and then plugging in the zeros or ones, and we showed each step right there. But once again, we're just kind of doing this now by taking the output if we do it for region other. And what will we take first? Well, we're going to call our double dollar signs to do the notation. And we're going to first say we're predicting frozen equals, we're predicting fresh, aren't we? Predicting fresh. Oh my gosh. Predicting fresh. And we're going to take the intercept right here. And then we're going to subtract from it the region other. So there's your intercept minus the region other, because remember we plug in a 1 right here for this. So that's what we're going to remove from it. And then we take the value. And then we go to the frozen, and the frozen has the coefficient of this. So plus this coefficient times frozen. And then we take milk. But remember, we have to use the interaction right here on milk. And milk is going to have a higher, it was negative to begin with. And the negative is going to be increased by the interaction value. And so this one actually is positive. That's where I was looking at the output and I was like, well, wait a minute. If this is the right model, milk should have a positive slope to it. But this is a multiple regression right now with 2 quantitative x's, which we can't really visualize very well. We'd actually like to put in implicit lines for this with frozen and stuff to make it work, which we just don't do that visualization. But once again, all I'm plugging in is someone says it's region other. I plug in a 1 for region other, and I solve through the equation. I plug in a 0 for region or Porto. A last thing to ask yourself is, what would be the equation for region Lisbon? Region Lisbon, which it wasn't listed for us to do, but we should be able to do, Lisbon would be, we are predicting fresh. It's the easiest one to write, so hence let's do it. We're predicting fresh right here equals the intercept, and then we would times this plus this times frozen. And since there's no interactions, we don't change the intercept because region Lisbon is the original one. And then we just subtract right here, and milk has no interaction on it because milk is not being predicted for one of the other regions like our Porto or the other regions. You would just plug in zeros for these, and this would zero out, this would zero out, this would zero out, this would zero out, and you're just left with this, this, and this because we're not in those other regions. Remember, those indicators can only take on values of 0 and 1, and once you get practice solving, you'd be like, okay, wait, I'm just going to plug in these values. We can make this look a little more pretty right there. But practice makes perfect. Try writing it out. Practice writing it down. I'm waiting until we get to the logistics stuff down here. I'm like, we've done so much interactions. The boss decides to use the model predicting fresh from all the other variables along with the interactions between region, grocery, and detergent, and groceries, all that good stuff, and grocery and meat. Fit this model using, the code. It's given to us right there. So we've got here the interaction between that, the interaction between that, the interaction between that, and then we have right here all the other variables. There we go. Verify the interaction between region and fresh is statistically significant using the drop one, even though individual variables whose coefficient slopes between the regions and references regions are not. What was that say? Even though the individual variables representing the interactions whose coefficients, oh yeah. So what it's talking about is we're looking at the region and frozen right here, and this is not statistically significant. So this means that the differences in slope for region Lisbon, for how it's predicting fresh based on frozen, is not statistically different than these 2 other regions, because we would compare it to the slope of region Lisbon because that's the reference slope, because it's the reference level of the region variable. So these both are not statistically significant. But in the drop 1, which removes out both of those from the model, hopefully we see it. And now right here, the interaction between region and frozen is statistically significant. So this is one of the biggest things to know, is that these don't matter. Rock, you rock.
It doesn't matter.
Those don't matter. We don't look at those. That is their statistically significant difference from the reference level, much like regions right here are statistically significant difference from the reference. Now, you will notice that we don't see region on here because we can't remove region without breaking model hierarchy. The only things that the drop 1 can do is it can drop one thing that does not violate model hierarchy. And what do we mean by model hierarchy? If you have region and frozen interaction, you must have region frozen in your model. That's why you don't see region being removed up here or frozen being removed up here, because if you were to remove frozen, you'd have to also remove region frozen to not violate model hierarchy. Model hierarchy states you have interaction between variable, you need the 2 components of that variable. And what do I mean by that? Here we are with the interaction between region frozen. Thus, we need the region variable right here, and we need the frozen variable in our model. So that means we have not messed up model hierarchy. And so, yeah, definitely. Verify the interaction between region frozen statistically significant. Yeah, definitely. We verified that. Run the C interactions on the model, determining for which region the impact on the relationship between fresh and frozen is the largest and smallest, assuming these customers are spending identical amounts. So we're looking at the interaction between fresh and frozen. Let's look at the output. The C interactions will be a better way to look at it, but we're looking at fresh and frozen. Fresh and frozen, okay. And we have an interaction on that? I guess we do. Here is, where's our fresh frozen interaction? Oh, okay, wait, here's the frozen, because it's, yeah. So the original coefficient of frozen is 0.79. But if we're in region other, it is higher by this amount. So region other is going to have the highest slope. Region Lisbon's going to have a slope like this. And region Oporto doesn't have a negative slope. That doesn't mean region Oporto has a negative slope. It means region Oporto's coefficient of frozen is this much less. So it's still going to be positive, actually. Still is a positive relationship. It's just this much less than the original coefficient. These are how much the coefficient of frozen will change depending on the region you are in. This 0.2177 means region other is that much higher than region Lisbon, which has this coefficient. This coefficient right here means region Oporto is this much lower than region Lisbon because region Lisbon has the reference level of frozen right there because it's going to be for region Lisbon unless we indicate we are in region Oporto or in region other. So once again, region other is going to have the highest, region Lisbon is going to have the next, and then a good bit below but still positive is going to be region Oporto. So let's see that through the output right here. C interactions, model. Woo! So many outputs. It said put the legend in the top left. Is it Loc or is it legend? Let's find out. Nope, might be Loc. We'll try this. Top left. Might have to review what the code has. And there it is right there. That's so tiny. Really? Well, I'll be little itty bitty graphic. We'll zoom in on it. Oh my gosh. But what do we see? Take a look at it. Oh, is it not? Where's our regions on it? Did something weird right there. What did we say? Remember how we said region? We got a lot of different graphics. We'll just focus on this one right here. We were saying how region, oh, we need the summary. Oh my gosh. Here we go. Region. That doesn't look like the right summary output. Here's our summary right here. There we go. Oh, a little more. There we go. Region other has the highest slope. There it is. Region Lisbon is a little bit below it because that's the reference. And then this one is not negative. I think most people are think that this one would be negative, that Oporto would be negative. But remember, Oporto's slope is that much lower than the slope of region Lisbon. This value right here is the slope of region Lisbon, and then the other is this much more above it, and then region Oporto is this much more below it, and if you subtract these numbers, you still get a positive number. 0.79 minus 0.62 is still a positive number, so we would see that right there, still a positive number. Ooh, now we're going to get into some indicators, some logistic regression. So let's switch over here. Get ready for logistic. It's about time for logistic. Let's do this. I'm going to clear the screen. Good review of quantitative regression right there, predicting quantitative variables. So we're going to start up some logistic. Let's do this. So here is logistic regression. That first part was a review of quantitative regression. And when we do logistic regression, we are doing a categorical Y. So we have 500 customers right here. And we're going to read in this file. Let's hopefully it doesn't have a -1 on it, right? Oh no, does this seriously have a -1 too? Let's go fix that really quick right here. We have an issue with the -1s. So we're going to fix this so it no longer has a -1. That's the acquisition. I do not know. I think these were re-uploaded. And let me change this right here. So it has no -1. So course documents. And that's Act 10. I did AC10. Act 10, customer acquisitions. Yeah, there it was re-uploaded. And there we go, save. And so that's fixed right there. Good deal. Now let's try it. Oh, I need to download it myself. So we're going to download it now myself. And I've downloaded it. Let's remove the -1 and it works. We are good to go. Problem's fixed. So reacquire, this is if we reacquire a customer, has levels yes, no. When logistic regression predicts a probability, which level is this probability for? We call this the level of interest. This is the level of interest. That is what we are predicting, the level of interest. This actually bolts the text, so I wouldn't knit this, but it really calls your attention to it. What is the level of interest? And the way to know what the level of interest is the level of interest is last alphabetical. Now, if you didn't know that, if you didn't know the level of interest is last alphabetical, we could make a logistic model. We'll be making more here in a moment, but so you might be predicting what the level of interest is. See if you know as I do this right here. Reacquire is the Y variable, not the data set. Be careful. If you capitalize it, you'll be using the data set. We're going to just look at offer right here. Y tilde X comma data equals. But here, that's got a capital O. Here's where the error occurs. This requires two different arguments. And we'll look at some different models here in a moment. We have to do family equals binomial. And this is because we're doing a two-level categorical variable. A lot of ways you can write binomial. It's pretty smart. It'll take it in quotes. It'll take it without the parentheses. But this works right here. I used to think it didn't work without the parentheses. But you'll notice we're doing GLM and we're doing family equals binomial. We are predicting a categorical Y. Must do. Number 1, must use GLM. 2, must use family equals binomial. And you don't need the parentheses. It'll work either way. This is where the errors occur. And you'll get your model, I think if you do it the other way, but it won't be right, because this is doing logistic right here. And the answer to which level it's predicting, remember the level of interest is last. So which of these alphabetically, H, A, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y. So which of these is last? Well, if you don't know which of those is last alphabetical, you can always view your model. And the answer is yes. So this is predicting the probability that somebody is reacquired yes. It's arbitrary, it's the last, and remember this, in reference or in indicators, reference levels are first, logistic, the level of interest is last. So with indicators, reference levels are first, in logistic, the level of interest is last. With indicators, reference levels are first, in logistic, the level of interest is last. Indicators are for categorical X's, levels of interest are for categorical Y's. So you have to have that written down, have to practice it, and know if I say the level of interest, we're talking about what we're predicting, like because we're interested in it. That's the thing we're trying to understand. And logistic is when we do a categorical Y and the level of interest is last. And then if we have indicators, that's when we have reference levels for X's and the reference level is first. So just remember that. We say I am first. When we do indicators, reference level is first. Remember this, pretty big right there. So we are predicting yes. Fit a model predicting reacquire from lifetime 1. Let's just take our model right here. Y tilde X comma data equals. And make sure to use that GLM. Let's go here and grab a lifetime 1, drop it in there. And there's the whole format right there telling you what to do. The formula is just the Y tilde X comma data equals. Get a summary and visualize it. Do customers who have spent more money before churning have a higher or lower chance of being reacquired? So this is how much money they spent for the lifetime. So we can visualize this to get the answer. It's not the model we're currently using. Or we can get the summary. And the answer is customers who spend more money are more likely to be acquired. And how do I know this? Well, between two customers who are otherwise identical, the one who has spent more money is more likely to be reacquired. And that's because this coefficient is positive. And notice how I'm interpreting this. This is how you'd interpret it on a test. Two customers who are otherwise identical. Well, it's not a multiple. Two customers who differ in how much they have spent over their lifetime. The customer who spent more is more likely to be reacquired by us. And just think about that. It's like investment in a company. If you don't see it yet, we can always visualize it. And the visualization of the model will show a positive sigmoidal shape. The positive sigmoidal shape here is once again indicated by the positive coefficient. If this coefficient here is positive, this will increase. Also of note, the negative intercept right here means at a value of 0, we would be predicting not the level of interest. So this is the point at which we flip to the level of interest. And I do want to make note of this. To find that, like you would on your homework, you take the negative intercept, put this as a note, the negative intercept over the slope and just divide them. And that point at which someone would switch is right there. And we can show this by going AB line and put a vertical line right there And you'll see it, that's the point at which someone would switch after they've spent this much more money over their lifetime. Not that they will switch, but we would predict customers in the long run who spend this much money over their lifetime would be expected to be reacquired. Not that one customer will, or if we get customers to spend more, they will, because it doesn't talk about cause and effect right here. Just that customers who spend above this region would be expected to be reacquired, where customers who spend below this region would be predicted or expected to not be reacquired. And that's what the summary is telling us. Look at the summary of the model. Which part of the output tells us this? The coefficient right here, the slope. It's going to be sigmoidal up. The probability required over lifetime in the same way you saw in the plot. Exactly. Using the numbers from the summary of the model, not the plot itself, at what value of lifetime 1 is there a 50% chance of being reacquired? And once again, we did this right here. I do want to point this out. Pretty good and quick equation to use. The negative intercept right here, which is B0 over the slope. And someone pointed out that you're basically solving the equation for when it equals to 0. And that's what you're doing. You're just finding at what value the slope and the intercept kind of converge if you were to add them to each other. Like if you were to add in a value of lifetime value, and I'll show it right here. If you had negative 2.691799 plus lifetime value, and then we take this value right here. Oh, wait, this is going to be this. That's the value of lifetime times the coefficient. You've basically zeroed them out. There's some decimals going on in the background we can't see, but for all intents and purposes, this is 0, meaning that we've basically solved the equation for 0. And that's because they kind of balance each other out. And we got that. Write out the equation for the logistic curve, the probability when a customer spends $400 per turning and reacquired. What is the probability for this customer? Now, this is where there's usually an error. This is where, trying to call your attention if you have fallen asleep or something. This is where people make a mistake. Because when we write this equation, we have to do the e raised to the over 1 plus e raised to the. I don't know if I have any notes open for that as of late, but it's e raised to the over 1 plus e raised to the. We're not using the regular old regression equation, but we kind of are. Let me explain. The equation right now would be, we take right here the intercept. Let's write the equation. So here is the regression equation. We are predicting reacquire. Sure. Did I spell reacquire? I think it is. Probability of reacquire. So prob of reacquire is equal to the intercept. Everyone gets so good at this. And they're like, no, don't change the rules. Plus this times this right here. Now, that's not what we're doing, though. I know I just wrote this out. We have to take this equation and do the equation e raised to the equation over 1 plus e raised to the equation. Reason being is we're not doing a line anymore. This is the equation of a line. So what we have to do, and I think I can do this with LaTeX, is we have to take, it's going to look pretty complicated for a second. We're literally just taking this equation going e, and I think if I do the brackets, I don't do a lot of LaTeX writing. Oh, there we go. E raised to the, and then it's frac, right? F-R-A-C. And you have to do a backwards, trying to make it look all pretty. I did. No, is it this one? There we go. E raised to the over 1 plus e raised to the. You don't have to know. Oh, what'd I do? I copied the wrong thing. There we go. E raised to the over 1 plus e raised to the. So that's e raised to your equation over 1. So that's still just the same equation. And here's what I like to do. Since this looks all complicated, the probability of being reacquired is e raised to your regression equation over 1 plus e raised to your regression equation. When I think of this and when I solve it in my head, I do the following. The regression equation solves out to x. So let's go here and take the regression equation right here. And let's say regression equation. 2 seconds. So let's go here and say x equals this. So I'm going to solve the regression equation right now for x. And then to make my life really simple, since the regression equation solves to x, I just go in here and plug in the x. And that's why you hear me say a lot of times e raised to the over 1 plus e raised to the. So I'm just going to solve the regression equation and then do e raised to that value over 1 plus e raised to that value. Much simpler than writing out the full thing because that's just the x is now just the regression equation. We've reassigned it. Much easier to solve. Let's solve the regression equation. Once again, that's not the answer. That's actually the logit answer. We won't use that. We're going to then take that number and do e raised to that over 1 plus e raised to that. This equation right here cannot escape the bounds of 0 and 1, which you see with the sigmoidal curve. So it's bound by the probabilities, and that's why we use this right here. So let's go ahead and take a look and plug in a value of 400. So all we have to do is go and take 400 and plug this in, and we have the value of x. I think we can literally grab this right here and take the equation, and we're solving this. And let's put it right there, and there's the answer. So the probability is actually going to be above 50%. You can also see that on the curve, that if you were to be at a value of 400, 400 is going to have some probability up here, so maybe around 68% or so. Once again, we're just taking a guess because now we're going to plug it into the e raised to the, and we're just going to grab the number. We could also grab the equation if we really wanted, over, and exp does the equation for us, 1 plus, now make sure to put this in parentheses, 1 plus e raised to the. I said around 68, I was pretty far off, but right here, if you trace up, that'd be about 64% it looks like. So in the 60s, I was 4% off, but we'll take it. So the probability would be 64% or so, 64.3%. Once again, make sure to solve the regression equation and then do the e raised to the over the 1 plus e raised to the. I cannot state this enough that it is a very commonly missed question when we say solve for the probability. People just put in an answer like this. That's not the right answer. That is the logit, because we have to then take that answer and plug it into the e raised to the over 1 plus e raised to, which we did right here. Just so you can see visually what I did, I took that answer I solved for x. So this was what x was equal to, and then I just plugged that in and did e raised to that over 1 plus e raised to that. Like if I'm doing it on a calculator, I'm going to do that. Probably most test relevant way. It's a little bit easier to do in R, but this is equivalent to had I just plugged this into the equation. Probably one of the harder things for people, what I've seen when people make a mistake in logistic. It's like solve for the probability, and then they just solve and say, this is the probability. No. You might say, well, isn't that a probability? Well, try this. Try plugging in 600, which is on the scale. If you plug in 600, you get the following. You get 2.23. 2.23 is not well, it's like 2.23%, or was that 0.64%? So you might still think you're good. Well, wait a minute. I'm still getting probabilities, right? Plug in 300. Now you'll know you're not getting probabilities, because when you plug in 300 as a possible lifetime value, you get a negative value. And that's because when you solve it in the equation, you'll actually get a probability less than 50%. So if we were to take this value right here that's now negative and plug it in and solve through the equation, the e raised to the over the 1 plus e raised to the, we will get a value less than 50%, and that makes sense. We should see on the curve here at about 300, it should be about 44%, and that looks to be pretty good right there. If you were at about 300, maybe about 44% or so. So that goes along with what we would think. Once again, this is where I see a lot of mistakes on the test. Like I've been teaching this class a while, and like usually solve for the probability, people forget to do the e raised to the over the 1 plus e raised to the, and I want to go back to the way I wrote it, because I really think once I realized writing it this way really helps. Solving it, that's just x. So you're just plugging in the value of lifetime, solving for x. Why is there 2 x's on there? Oh, So what did I do? There we go, okay. So this is the value you're solving for. Whatever the regression equation solves out for, it's technically the logit. Don't worry about that. We won't quiz you on that. But you're solving for this and then plugging it in here to get the probability. So it's like a 2-step thing. I think it makes it easier just to solve. So biggest help I can give you on that right there. Fit a simple model, predicting require from offer. We did that earlier. Value of offer, visualize fitted logistic. You'll notice that does not look like a logistic curve and looks like a straight line. This is because we're only looking at a small range. Change the X lim inside. That's how you do on the visualize model. So extend the range of the plot. Although these aren't viable values of offer, you can see that we are indeed using logistic curve. So we saw this earlier, and I've had people tell me, wait, is that the logistic curve? And it is, because when you see the logistic curve really close up, you might be seeing a portion that looks like a line. Like over here, it would look like a line if you zoom in on it. So let's go ahead and take our model right here, and it looks like a line until we change the x limbs on it. The x lim takes two arguments, it's one argument, but it takes two values inside of there to change it. Now, we don't have values to -20, but this is, of course, the logistic curve. But when you zoom in on it, like if you zoom in on a value between +20 to 40, you're going to see what looks like a flat line right there. So once again, zooming in on it right here, between 20 to 40, you would see the flat line right there, which we don't really care for. It is a bit naive to study the relationship between the probability of acquiring a customer and the amount of money spent before churning with a simple logistic model because there are lurking variables. Other reasons why the probabilities may differ, like gender, age, all these different things right here. Fit a model predicting from all these things right here. Look at the summary. Among otherwise identical individuals, does the individual with the larger value of lifetime 1 have the larger value of smaller based on reacquisition? All that good stuff right there. Let's go grab our model. We've already got a good bit written. And which variables do we want? We want to grab here all these variables. So let's go right here, grab them. And all we're going to do is start turning these into variables to make sure we get the right ones. So we have offer plus lapse plus percent change. And what I'm going to do right here is I'm actually going to hit enter and go to a new space right there. Oh, there we just need a few more. Plus age. And it's mad about those. We're just adding in the variables and go there and sure. Just depending on how you want to make your code look, you can go y tilde x. There's all my x's. I'm going to put the data equals on a new line. So y tilde x, comma data equals, comma binomial equals. Code looks a little bit nicer now, a little bit easier to read. And there's our model. Let's go ahead. We cannot visualize this model, but we can get a summary. And let's look at the, did we not put, oh, wait, where's lifetime 1? Lifetime 1, I'm so sorry. There we go. So now with lifetime 1 in here, lifetime 1 is super significant. That's how much money they've spent over the lifetime of their contract. Wow, that's ridiculously significant. It's at a ridiculous p-value. A lot of these are very significant. Gender not significant. Price change not significant. Lapse is significant. And that's if they bring new information, reduce the deviance of this model away from the null. And with this right here, lifetime 1, we see here that the customers who are spending more between two otherwise identical customers, because this is multiple regression now, the customers who spend more money over their lifetime are more likely to be reacquired. But what's really weird is the older contracts are less likely to be reacquired. So if you're well, that makes sense. If you're an older contract that doesn't spend much money, you're less likely to be reacquired. You kind of been like, I'm done with this company. So you've been with us a while, but you don't spend much money, you're less likely to be reacquired. And that right here is the age. Between two contracts that are otherwise identical, the ones that are older are less likely to be acquired. So please listen up to this too. Never mention the coefficient when interpreting in logistic. Only mention the sign. More or less likely level of interest. You'll never hear me mentioning this value because the change is not a constant change. More evident when we see the curve looking like this, you can't talk about 1 unit differences. You can just say something is more likely, or if it was sigmoidal down, which we haven't seen a sigmoidal down curve today, but if it was sigmoidal down, then you would say they're less likely if they have higher values. So between two customers who are otherwise identical, where one has a higher values of offers, the one with the higher values of offers is more likely to be reacquired. We offer people more, they're more likely to be reacquired. Kind of makes sense, like, hey, we'll give you this much more if you come back. Hey, I'll come back. So makes sense with our world. And we're talking about otherwise identical customers, like they've been with us the same amount of time, like age of the contract's the same, their price changes are the same gender, same lapse in contract that they've been gone for a certain amount of time, and same lifetime spent. When we offer these same identical customers, like we have two customers that have the same sort of contracts with us, but one of them is given a higher offer than the other, the customer who gets in higher offer is a good bit more likely, definitely statistically significant, to come back. It's one of the stronger coefficients in the model when you look at the weight of the coefficient. So I'd say like offers is something we really should investigate more and probably run some trials on to see how offers are impacting our reacquire rate. And this is where it really applies. This is when you think about it, people might say, well, maybe it's just the people who haven't been with us a long time are more likely to come back. And you say, no. This is a multiple regression. We have the age of the contract in here. So if it were people who have been with us a short amount of time, that's under, we are controlling for that variation by including it in the multiple regression model. So there's two otherwise identical customers. They've been with us the same amount of time, but one of them gets more offers than the other. The customer who gets more offers is more likely to be reacquired. They say, well, wait a minute. What about if they just have lapsed longer, but we give them a higher offer? You say, no, it's two otherwise identical customers. These customers have the same amount, theoretically, mathematically, the way we solve it, have the same amount of lapse in their contract. So everything else is identical between these customers, but one customer is given more offers than the other. The customer that gets more offers is more likely to be reacquired. And that's what's really great about the multiple regression. It's because we're considering the other variation and holding everything else constant. Well, that's got it right here. A lot of great solves. Make sure you understand what's going on with Logistic. I think that's got it for today. We're going to head off here, but if you got questions, let me know. Keep up the great work. Good activity. Practice that Logistic. It's a little bit different, but a little bit the same. I guess the last thing we should look at here is the check regression. Why have we not done a check regression on this? Let's go here and run the check regression. I'm going to run two more codes right here. Bonus code. Was this model the proper fit? The answer is, whoa, I've never seen that have a p-value. This is a good thing. These p-values here are excellent, telling us that the logistic model we just fit is a good model. So these models right here, excellent fits, great models, good stuff. Use the models. If the p-value was low, we'd have evidence they are a bad fit. This is a check regression where high p-values are good. We believe the model's good until we have evidence it's bad. Good p-values. One last thing we didn't see in the code today was making predictions with the logistic. I've done this during class, but I want to do it right here if you're watching the video. If you want to make predictions with logistic, you need to make new data and store a data frame of your X variable. So I'm going to put in here the lifetime value equals to the vector of 300, 400, and 800. And now we go predict using our model. Let's rerun this model. And we're going to put in here new data equals new data. And then type equals response. Hey, Ditto, great to see you here. 100 points in the chat. And what this is going to do is it actually gives me the predictions. If you remember from earlier on, we got the probability of 64.38%. And so all that work we did where we were solving out the probabilities earlier on could be done also by using this code right here. So the reason I show this now is if you're doing the assignment, you could find the probability of somebody with a lifetime value of 300 being reacquired, the probability of somebody with a lifetime value of 400 being reacquired, or 800, and notice how the probabilities increase right here, and that's not the reacquire curve. Follows the same pattern. Here's the lifetime curve, and we can see the values right here. This is how to do it with code using the predict function right here and type equals response. If you don't do the type equals response, you will get the values that the regular regression would get for predictions, which is not correct. Remember, these values have to be put through the equation e raised to the over 1 plus e raised to the. So this would solve for x right here, and then type equals response as the additional argument solves for the probabilities. And that's got it. Just want to show those last bits of code. Like, what code did we not do? We didn't do the check regression. We didn't do the predict. And we did the drop ones and everything. But stay tuned. Ask those questions. Keep up the great work. 100 points to end off right here. That's got it. We'll be back next week. But email me those questions and let me know what you're thinking. Bye for now, everyone. Bye.